Good day, everyone. Once again, we're back together, just looking at the DBE November 2021 paper. All right, so we're going to be looking at question 7 of it. And yeah, for those of you who haven't subscribed, please just be part of the family. And obviously, for those who've just written this paper, please, the purpose is not to stress you out in any way, but just to quickly review the questions that were part of our exams. Okay, so for those of you who need assistance with mathematics or physical science, please, you're more than welcome to get in touch with us, and our email address is info@mlungisinkosi.co.za. All right, so let's get into question 7 based on electrostatics. Okay, so they give us a small sphere a small neutral sphere rather acquires a charge of minus 1.95 times 10 to the power minus 6 coulombs. Okay, now remember that when we've got a negative charge, what it simply means is that we've got an excess of electrons, right? So it means that we've got more electrons than protons. All right, so they're asking here in 7.1.1, were electrons added to or removed from the sphere? Okay, so obviously it means that because we've got an excess of electrons, it means that electrons were added. Okay, so that's the first one there. Now, so in 7.1.2, okay, they say calculate the number of electrons that were added or removed. Okay, so what we'll simply do is that, remember, we've got a formula, but it's not really a formula per se. So in 7.1.1, we said they were added, okay, and in 7.1.2, they said calculate the number of electrons. So we have the formula that says the number of electrons, it's the charge divided by the unit charge of an electron. Okay, please remember that unit charge, formula is that unit is actually given. Okay, so that's 1.95 times 10 to the power minus 6 divided by the unit charge of an electron is negative 1.6 multiplied by 10 to the power minus 19. Okay, and let's find an answer to that. And our answer is 1.22. Okay, to the power minus 19. So that's 1.22 times 10 to the power 13 actually. Okay, and remember we're looking for number of electrons, so that's electrons. Okay, just to keep in mind for those of you going to be watching in future, of course, when we talk about the number of electrons, we always need to make sure that it's positive. You cannot talk about negative, something electrons. So sometimes if this was a positive charge, so you would need to actually divide by positive 1.6 there and actually get that number there. All right, now let's keep going. Okay, so they say define the term electric field at a point. Okay, so sorry about that. So they say so electric field, this we simply say this is the area in space, right, where electric charge is felt per unit charge. Okay, so this is the area where electric charge, or electric force rather, electrostatic force is felt per unit charge. Okay, so let's go to 7.1.4. I'm not going to write that down. They say calculate the magnitude of the electric field at a point, right, 0.5 meters away from the center of the charged sphere. So remember how we simply calculate electric field. We say E is equals to K multiplied by the charge divided by the R squared. So this is going to be 9 times 10 to the power 9 the charge was given as 1.95 times 10 to the power minus 6. Okay, and we say divide that by the unit charge, the distance rather between them was given as 0.5. Okay, but remember to square that distance. Okay, so let's get the answer there. And I get an answer of 70,200. Okay, newtons per coulomb, by the way. All right, and in this case, if you wanted to specify direction, of course, it would depend on where. Okay, they just said magnitude, so we're just going to leave it like that. All right, as we move right along now, they said we've got 2 points. Let's go to 7.2. 2-point charges Q1 and Q2 are fixed 0.02 meters apart. Okay, so there's the diagram there that illustrates that scenario. They say the magnitude of Q1, of charges Q1 and Q2 is the same, and Q1 is negatively charged. Okay, okay, so they don't tell us about Q2. They say the small charge sphere with the charge of minus 1.95 is placed at point P. Okay, so there's point P there. All right. Okay, 0.03 meters from the east. Okay, of Q2. And then in the diagram, as shown in the diagram below, they say the spheres at point P experience a net electrostatic field of 1.38 newtons to the west. Okay, right, now they want us to calculate the magnitude of the charge on Q2. Right, so we're just going to look at this scenario and check, all right, what exactly is going on, right? So the first thing that I notice is that so the charge, the force, let's say the force, if we're to look at Q1 and Q2, the force that Q1 would exert on Q2 would be a force of repulsion. So where would Q2, what would be the direction of the force that P experiences because of Q1? It would be a force to the east, because it would be repelled away, right? So that the net force ends up being in that direction can only attest to the fact that Q2 must therefore be positive, and it must actually be a force that is bigger than that of Q1. All right, so let's do the following. Let's say, okay, let's find an expression for, you know, the force that Q1 exerts on P. Okay, so I'm going to say, well, the force of Q1 on P, all right, this is going to be K Q1 times QP divided by the distance between them, r squared, right? So I'm going to say, okay, this is 9 times 10 to the power 9 multiplied by okay, let me substitute the charge QP. All right, so 1.95 times 10 to the power minus 6, okay, multiplied by the charge of Q1, okay, divided by the distance. Now the distance between the two there, remember, between P and Q1, that's 0.03 plus that's 0.02, so that would be a total of 0.05 meters. Okay, and obviously we can square that. All right, if you want to, we can simplify that. So that means that if we wanted to find that force, okay, let's just find the product there. Okay, get a huge answer, 7,020,000. So I'm just going to express it in scientific form. 7.02 times 10 to the power 6. okay, multiplied by Q1, remember? So that's our expression for the force. Okay, now what I'm going to do is exactly the same thing when it comes to Q2. By the way, I do know that this force, remember, we did say it's a force of repulsion, so this must be eastwards. Okay, and then let's find now the force between Q2 and P. All right, we're going to use the very same formula. So FQ2, in fact, I'm supposed to use a small p, q there, times QP divided by the distance between them. Okay, so again, so this is going to be 9 times 10 to the power 9, multiplied by, again, it's going to be 1.95 times 10 to the power 6 times Q2, the charge on Q2, divided by, and the distance between them now is going to be just 0.03. Okay, all right, and remember we're trying to find just an expression for that. Okay, so let's find that, and I get an even bigger number. Okay, so when I express it scientifically, 1.95 times 10 to the power 7, remember, multiplied by Q2. Okay, so that's newtons, and in this case, as I did say, that the net force is that direction must mean that Q2 is actually exerting a bigger force. And I mean, of course, we can already see that to some extent. So this would be to the west. Okay, right, now let's get to just the conclusion part of it. So we know that the net force would be actually the difference between the two. Even if you wanted to take a positive direction, say you took west as positive, or you wanted to take east as positive, ultimately it means that my net force, okay, so E net would be equal to maybe let's if you want to, let's take west as positive. Okay, since our net force is to the west, so it's going to be actually E2 or EQ2 on P minus the field, the force. Why am I saying the net field rather? I'm so used to talking about net field so much. So that's F net is equal to F. Okay, so this is going to be the one that has 1 on 2, right, on P. So I'm sure you already can see how the cookie will crumble there. Okay, so what I'm simply going to do, sorry about that clutter there, so I'm going to substitute for my force, so that's 1.38. okay, remember that Q1 and Q2 we were told that have the same magnitude, right? So what we can actually do is that, in fact, let's write down the two expressions. So this is going to be, this is 1.95, not 7. Okay, so that's 1.95 times 10 to the power 7. Okay, Q2. But remember that Q1 and Q2 have equal charges, right? It's just that the one is positive. So we can actually both express them as Q1, okay, minus 7.02 times 10 to the power 6, okay, also Q1. Okay, so all we need to do is just take Q1 out as the subject of the formula, take the difference, and we divide that 1.38 by that difference, okay, and in this case we will get our charge. Please just verify the answer for me. Let me just work it out quickly. Okay, and I get a charge of Q1 which is equal to Q2 in terms of magnitude, by the way. And let's actually express, in fact, you know what, let's just find the charge of Q2 because that's what we're asked to find. So I get a value of 1.11. Okay, it's 1.105. So I'm just going to say 1.11 times 10 to the power minus 7 coulombs. Okay, and please remember this Q2 must actually be a positive charge. Okay, right, and sorry about that little mess there. Okay, but I hope that you can actually just appreciate that the fact that in this case, so we've got 1.95 there, and it's subtracted with 7.02. Okay, just note the exponents there, and in this case, yeah, look at, I even wrote power positive 6 there, but I calculated it correctly, I know that. Okay, right, so I got the final answer to be 1.11 times 10 minus 7. Please let me know if that is what you get as well. Okay, right, and essentially that is how we would have gotten ourselves the full 14 marks on electrostatics. Right, and I hope that you enjoyed this episode, ladies and gentlemen. And please don't forget to tell, just more and more of our grade 11s and those who want to upgrade, about our channel so that they can actually, find value and benefit from it. Okay, otherwise from me for now, I'll see you guys next time. Sharp, sharp.